So I'm Nate Mathews, and I'm excited to present our work on evaluating efficient website fingerprinting defenses. This work was produced in collaboration with a number of my colleagues from the Rochester Institute of Technology, the University of Minnesota, and Ewha's Women's University in Korea. Nowadays, we face many potential threats when browsing the internet. In particular, journalists and activists are common targets of scrutiny by authoritarian regimes. This motivates the need, this motivates the need for privacy and anonymity, for which many people are turning to Tor. Tor works by adding intermediary hops to communications between the client and the target server. This prevents eavesdroppers from being able to trivially associate the client with the IP address of the endpoint. However, an attack known as website fingerprinting may undermine this security. In a website fingerprinting attack, an adversary eavesdrops on the traffic between the client and the Tor network. The attacker uses metadata of the traffic to train a classifier model to predict the visited website based on patterns in this metadata. In response, there's been a recent emphasis on trying to find a way to protect against this. And we can do so by manipulating the traffic on the vulnerable link between the client and server. This manipulation, however, has costs, so there is a great concern surrounding the trade-off between security and efficiency of the applied defense. And so this is the premise of our paper. We examined many of the notable defenses proposed at the time of this project, and we constructed a taxonomy of defenses to better understand their construction. We evaluate 9 of these recent defenses using a state-of-the-art deep learning classifier and use timing and directional information. We will begin with reviewing our taxonomy of defenses. For Tor, there are 3 fundamental mechanisms that a defender can use to manipulate the traffic metadata. First, we add we can add dummy cells to the traffic stream to modify features such as flow rate and burst patterns, although this comes at the expense of adding network congestion. Alternatively, we can add timing delays to real packets to manipulate patterns, but at the cost of slowing the speed of the page load with every delay that we add. And then finally, a third option is to split the stream across multiple streams, which each stream being fed through different channels. This has numerous advantages, but may be trickier to do. Now, we can apply these mechanisms to develop defense strategies. The design of the defense strategy is critically important so as to provide the most amount of defense at the least amount of cost. If we look at the literature, we find that we can organize defenses into 5 broad categories. These are fixed-rate traffic sending, random padding, targeted collisions, and traffic splitting and adversarial defenses. We will look at each of these strategies and associated defenses briefly in the following slides. So first, the basic idea of a fixed-rate traffic sending defense is to use packet delays and packet insertions to schedule traffic at a constant rate of flow. This strategy can be very effective at eliminating privacy leakage, but often at tremendous costs. Dynaflow does this more efficiently by adjusting the targeted flow rate to the real flow rate within fixed windows. So next we have a very popular defense strategy where we only insert fake cells into a flow using some sort of stochastic heuristic. This helps to avoid page load delays that would impact the user experience. And we have 4 defenses that fit here. The first, deep fingerprinting defense, uses packet insertions to extend the size of directional bursts by a random percentage of the burst size. Front uses target insertions to add a higher density of dummy traffic to the early portions of a website load. And spring and inner space defenses utilize a state machine to adaptively insert cells into gaps within traffic. Up next are the targeted collisions category of defenses. Under this strategy, we manipulate the traffic sequence with delays and insertions to imitate a profile of a different traffic sequence to efficiently cause confusion. Early defenses followed a strategy rigidly, trying to rigidly match a target sequence, but this turned out to be fairly infeasible to implement in practice. So the bimorphing defense improves upon this by using a stochastic padding machine to imitate the distribution of bidirectional bursts of a profiled site. Now, this defense has a major downside in that you have to maintain a profile list and distribute it across clients. The 4th defense category is the traffic splitting category, which performs no packet insertions or intentional delays of packets. There are 2 defense proposals here, HYWF and traffic sliver. Well, both defenses use different heuristics to determine the stream on which they send the packets. The key differences here are the number of splits they use and the channel that they send them over. So now our last defense category, adversarial perturbations, leverages vulnerabilities in classifier models called adversarial examples to efficiently trick the model. The basic concept here is that small, imperceptible noise vectors can be generated that shift the sample into a different classification boundary. This can be adapted to network traffic by instead generating vectors of adversarial packet direction and timing delay perturbations. So Mockingbird does this for direction-only perturbations in an offline manner, and blind adversarial network perturbations applies it for both timing and directional perturbations in a more generic manner that can be applied on live traffic. So now we can examine these defenses under a gauntlet of experiments, so they can be cross-compared in a like-for-like manner. And in the remainder of the slides, we'll go through the methodology and some of the key results. So to evaluate defenses, we utilize a deep fingerprinting convolutional neural network with the TikTok feature representation. Aside from its state-of-the-art performance, at the time we selected this model because its feature representation captures both raw timing and directional information, which accounts for all the relevant raw information in core metadata. Now there's one exception to this. For the fixed rate Dynaflow defense, we use a modified feature representation that better captures the available information in the fixed rate flows. We found this worked a lot better for the DF model. So we follow the standard scheme of simulating, training, and testing website fingerprinting models. This is to say we split our data set into train, test, and validation portions, then apply the defense simulator to all portions using the same parameters, before finally training and testing the model. Now, when we evaluate any of the stochastic defenses, we do some additional data augmentation. Rather than simulating only one defendant sample for every sample in the training dataset, we apply the simulation multiple times to produce multiple defendant samples. This allows us to scale up the size of our training data substantially. I should note that we're not the first ones to do this. Tobias Poles applied the same strategy when he evaluated spring and interspace defenses previously. And for the front defense, we expand on this idea by restricting the number of unique source samples used in earlier training epochs with the intuition that we would be able to try to teach the model to predict the padding distribution by limiting the number of unique possible patterns. And you can see the full paper for the full details there. So website fingerprinting is evaluated under two settings. In the closed world setting, the model is trained to predict sites within a constrained set of monitored sites. A more realistic setting is the open world setting, in which the model is evaluated on its ability to discriminate between the monitored set and all other websites. To evaluate this, we collected a new data set. We call it the big enough data set. The data set contains 95 websites in the monitored set and 19,000 samples in the unmonitored set. We collected this data set across 3 different security modes in Tor. And we also collected a separate traffic sliver data set to evaluate that defense. So let's look through the closed world performance. First, we see that the best performing defenses are Dynaflow and traffic splitting defenses, reducing performance to around or below 50%. Next, we see that defenses that rely on some stochastic packet insertion cause only a modest drop in performance, falling in the range of 75 to 80% accuracy. And finally, the DFD and BANP defenses perform especially poorly, comparing similar just to the undefended data. We also found that fingerprinting performance remains similar between the different security settings across most defenses. And so now we can use these results to kind of motivate our selection of these 3 defenses, interspace, front, and traffic sliver, as forming a sort of Pareto front amongst the defenses we reviewed. So moving on to the open world evaluations. On the left is the full precision recall curve in the standard security mode, and on the right, we highlight results with just high precision. If we, again, just look at the stochastic padding defenses, we see that we can still achieve both high recall and high precision, and they all compare similarly to one another. Next, the traffic splitting and Dynaflow defenses still perform well, reducing recall to a completely unusable range. And finally, the BANP defense does, again, really poorly. I want to take a moment to highlight why that is. The BANP defense was originally proposed under a different attacker model, where the attacker doesn't train a defense-specific model. But as you can see, when we do train a model on these adversarial samples, they lose their adversarial properties because the model learns the adversarial noise. So next, let's look at overheads incurred by the defenses. On the left are overheads computed by comparing the total number of delays in the insertions across the entire data set. And on the right, we instead take the geometric mean of the per trace overheads. We do this because large traces dominate the total overhead estimations, so it's important to get these two perspectives. As we can see, some defenses, such as front, are significantly impacted by the per trace overhead is considered. Overall, we see that overhead still remain quite high, despite these defenses ostensibly being tuned for efficiency. Now, finally, perhaps the most important aspect of a defense is how realistic it is for the developers to be able to implement and apply it in practice. There are 3 different pathways that you can implement these defenses. These include the use of the pluggable transport system in Tor, or the circuit padding framework in Tor, or separately devising a bespoke custom solution. Now, the preferred mechanism is the circuit padding framework because it's built directly into Tor and designed for padding defenses, but it's restrictive. We don't have time to go into the full details of the limitations here, but all of the defenses fit into one of these 3 categories. So in conclusion, our analysis identified a number of concerns that are still present amongst the defenses we reviewed. But with that said, I want to highlight that a defense does not need to be ideal. It just needs to be well suited for the constraints of Tor. What I think the space is still missing are defenses that are easily implementable and truly efficient and target just enough security to make website fingerprinting impractical in the real world setting when you have millions of websites. And with that, I can take any questions.
Questions?
Sorry, maybe just understanding the premise of this. In your paper, you say this allows a passive local eavesdropper. Can you explain just the front end of this, of how you insert yourself or where that attack is?
So, and specifically with the way that we collect the data set, we're imagining a threat scenario where the first node in the 3-hop circuit that represents a Tor relay is probably compromised and is sniffing your traffic. So in the traditional kind of Tor threat model, we assume that if any of the adversary or the nodes in the circuit are compromised, that's still okay because they don't see the full path. But if the first guy is compromised and he's collecting your data and applying this website fingerprinting attack, he can potentially de-anonymize your traffic without seeing the full path that your communications go through.
Any other questions?
So this work, being that Oakland goes through this journal model, was completed a fair bit ago. Have there been other defenses published since the work was completed, and do we have?
Yes, there has indeed. There have been a number of defenses. We've picked out, it looks like 5 of them to take a look at from 2021 to 2022. A couple of things to note is we've seen 3 more adversarial style defenses. These are the Surikov, Dolos, and Minipatch. We probably can't go into too much detail here, but Surikov at least claims to kind of improve upon the BANP and is able to still function in the presence of adversarial training, which is pretty cool. I've not looked into, we've not evaluated any of these defenses, to be clear, in our presentation, just presenting them as other stuff that's out there.
I have one question for you as well. So if you go back to your last slide, so you mentioned about, you raised a question about at what point is a defense good enough? Mm-hmm. And I wonder if just settling down at a defense that is good enough for the state-of-the-art attacks is a good strategy, or you think that we need to do something better in a more principled way to kind of anticipate also the attacks that might be coming up in the future? Yeah,
that's a good question. And it's also, I think, a difficult question to assess. So in the website fingerprinting setting, we're especially concerned about false positives in practice, because the base rate occurrence of any of these monitored sites in our set is going to be really low respective to the full size of the internet and browsing that goes on. So you can get away with potentially just small errors in the attacker model in our more constrained lab experiments that will produce a much larger error in practice. And now, in addition to like kind of separately from this, Tor is really limited in the amount of additional bandwidth overheads that it can tolerate. So in practice, we're going to be constrained to really small overheads that we can even add without causing a big disruption to the network. But those small disruptions might lead to bigger disruptions in the context of the really big open world settings that an attacker has to realistically handle. So what I think we probably need is just a really big data set to kind of evaluate this more realistic setting in at some point in the future.
Okay. Any other questions? Right. Let's thank the speakers.
Thank you.